Well, thank you very much, Arturo, for the introduction, the kind introduction, and also for the people organizing the event for inviting me here to present something we are proud of, something we started in 2015 together with India. And it was a journey that we never thought it was going to be so fruitful and successful as 5TONIC has been. I would like to give you in the next 20 minutes a view of what is the objective of 5TONIC, what have we achieved so far, how we are working, and also what is also important, what is our view to the future and next steps in this initiative. Well, first, a bit the spirit of 5TONIC, no? It's we call it an open co-creation lab, where we try to make use of the technology and develop technology, and do this in many different phases of the technology development, from the basic research, where we explore new 5G components and new 5G technologies, usually in the scope of European research projects, through all the process down to taking this technology to the industry and work with industrial partners to see how we can apply this 5G technology in real use cases. No? And we go through all the phases in the process. It is also very important the work we do on dissemination of everything that we do, both in the academia, so as with master classes in different subjects, and also in collaborating with students from Carlos III University in Madrid. We also offer in the lab demonstration of many of the 5G and 6G projects in which we are participating. The lab is supported by a number of companies. Some of them are permanent members. You can see there the 7 that are right now in the board, with Telefonica and India being the founder members, and then Ericsson, Universidad Carlos III de Madrid, Comscope, Interdigital, and Capgemini as permanent members of the board. You can also see a big list of collaborators, many of them collaborating with us for a long time. And they do some activities in the lab, principally on a temporary basis. Okay, so just for joining us and collaborating in specific activities. But again, some of them has repeated over time, over several years, and this means they see a value on the work we do in 5TONIC. Again, the activities we run, as I said at the beginning, are classified probably in 4 categories. No? One is the development and testing of 5G use cases, and we do this with partners from the industry. You will see later on how we have addressed most of the segments and most of the possible applications of the 5G technology. We are also a stream of work on trying to test and evaluate certain 5G components. The last one has been the testing, for instance, on end-to-end slicing together with Ericsson. And here it's important that in the lab we try to be a step ahead of what is in commercial production, and we bring components that are in earlier phases of the development. Finally, and this is probably a good basis of all the activity in 5TONIC, is all the work around the European research projects. No? All the members in 5TONIC participate in these European research projects, and 5TONIC for us is the place where we together run many of the activities that we commit with the European Commission around these initiatives. And finally, as I said, we also run workshops, master classes, and a number of dissemination activities to try to, show and share with the rest of the industry all the work that we are doing in this lab. Yeah, we are following something, a way of working that probably is a reference in Europe that is based on projects. No? We have members that in general are very active, are proposing new activities and new projects to the board that once approved are launched and executed. using the resources that the members provide. Okay, the lab already has a permanent infrastructure that we can see that is available for any activity, but members are bringing additional resources as needed for these activities. No? In general, most of the work, or a good part of the work, again, is based on European projects that are funding part of the activity we run. This is an example. So the list that we keep of activities ongoing, activities we closed, this is something that is permanently and dynamically changing. So 5TONIC is a very dynamic lab in this sense. And here you have, for instance, examples of different partners in the different vertical industries with which we have collaborated. You can see that that goes from gaming, emergencies, manufacturing, utilities, financial, education, automotive. So almost all sectors have been represented at some point in time in 5TONIC. They have collaborated with us to show how the 5G technology can be applied in the specific use case. And for this, we have found all kinds of different partners, from technology partners to, again, business and industrial partners that are essential for us also to understand how the technology that we are developing and working with and exploring is applicable to different use cases, again, in the different sectors of the industry. And here you have some examples of the last ones that we have developed in the lab. One of the virtualization of the controllers of the automated guided vehicles in factories. It's an activity that we have been running in the last years with ABB, formerly ASTI. Also, the 5G best fast response emergency service that we run with the health authority in Madrid, SAMUR. Very recently, we showcased, it was in July in 5TONIC, the connected vehicle prototype that was developed by Capgemini in 5TONIC and connected to the 5G network and the edge computing platform we have there. Zero defect manufacturing applications, also 5G in this area, in the industrial sector with Innovalia. Applications of 5G to gaming with NVIDIA that were pretty insightful in terms of how the 5G network can be fit for a better gaming experience. Virtual and augmented reality, in this case with a startup, Yerbabuena VR, that help us in showing how this technology can be used in real-time streaming of live events. And finally, something that is not very usual. So we have seen drones and connected cars, but connected vessels. So it's something that in few places is done, and it was done also in the 5TONIC lab. As you can see, a wide variety of different use cases that give us a lot of insights of what were the requirements of the industry in terms of the 5G application. We are also evaluating technology, and this is also relevant, beyond what is in the standards. Okay, and we have examples, for instance, with Cohere Technologies, a startup that brought to us OTFS, that was a new waveform that was providing a higher spectral efficiency on the antennas that is now taken to standards, by the way. We have tested new antenna technologies and also new signal generation based on optical processing. So a number of new capabilities that is important to us for keeping the lab always ahead of the technology. Typical work we have done has been also on areas like network slicing or the 5G standalone core to understand how these new technologies bring in new capabilities. And this is just to show a bit an example of the different 5G projects that we have been running in the lab, or part of the activity being run in the lab, both inside the EU and also in collaboration with other countries like Brazil, Taiwan, or China. And also some of the first projects that we are starting in 5TONIC, inside the 6G SNS program. You can see the TrailsNet, Predict 6G, the second phase of XAX, and Desire 6G. So these are 4, but the members of 5TONIC have already been approved for many other projects that will also be running activities in 5TONIC. This is a diagram of the lab. It's a complete lab, so of course you cannot read anything, but there you have all components of a 5G network. You have a complete 5G core, you have edge computing infrastructure, you have all kind of indoor and outdoor radios in 4G, 5G, in all kind of frequencies. So this is really a complete setup where basically any kind of 5G use case can be run. We have also testing tools, of course, to support the different use cases and technical component testing. This is the aerial view of the facility. So we have labs in several buildings, but also a space outdoor where we can make testing. For instance, in this outdoor space, we showed the vehicular communications with Capgemini in July. This is also a snapshot of one of the rooms where we are testing. This is very important as well. Our lab is portable, so we can take the 5G network anywhere. So we have portable 5G systems, so that allows us to test beyond our facilities to any city or province in Spain. This is another example of the lab where we are integrating the robotics into the 5G network. Our data center, where we are hosting servers from the different members and also from India. And important, the expansion we are at this moment planning and realizing from the lab that you have seen in the picture in Leganés to the campus of the Carlos III University in Madrid. And that has been what we have done so far. No, but we are at a moment in the lab where we want to start thinking forward and also thinking what is coming next. The lab in 2015 was dreaming on having a full environment of 5G for running use cases in different industries. We already achieved the target that we had in 2015, and now we're setting the next objectives for the next years. And we were thinking beyond 5G, what is coming. No? Of course, there are a lot of new characteristics that 6G will bring. Of course, this means new capabilities. This represents that we'll have new technological components to test in the lab. Okay, I don't want to go through the details, but 6G is coming a lot of new technologies and new architectures that we'll have to test in the lab. And what is more important, all these capabilities beyond 5G and 6G will also enable use cases that today are not possible with 5G. No? And this will be also one of the targets when looking at the future towards 2030. This is just a short list of the first projects that are bringing activity to 5TONIC, some of them inside the Spanish Research and Development Program, UNICO, others as part of the European framework of 6G SNS. And in all of them, we are bringing, again, new capabilities, new use cases, and new opportunities to test technology developments. These are probably the kind of use cases that we foresee will be more relevant in this new phase. The first one is associated to industrial sector. And everything related to time-sensitive networks, deterministic networks, RedCap, reduced capabilities, devices with reduced capabilities for massive IoT. So this is one of the areas of probably expansion of our activities. The second one is related to video analytics, but beyond video analytics, everything related to artificial intelligence at the edge or real-time artificial intelligence. Also, metaverse, anything related to the extended reality in different environments, consumer, business, or industry. Artificial intelligence again, and the application of this artificial intelligence to autonomous networks, or how can we evolve, the networks to networks that are able to learn the behavior of the different applications, the behavior of the traffic, and also in closed loop adapt the configuration and adapt the the characteristics of the network to meet the new demand. And finally, something very important, everything related to security and start introducing safe networks for the post-quantum era. Okay, there is a threat that is always foreseen in 5 to 10 years that quantum computing is there, that will be a threat or to breach all the encryption that we have today, and we are trying to start, doing activity for preparing for that time, no? With post-quantum cryptography, quantum key distribution, and other technologies that will allow us to come to a future in which we see pervasive sensing. So the telecom networks used to sense what is around, with computer vision and artificial intelligence at the edge, again, providing additional capabilities to business customers, to the customers, but also support for extended reality, for biosensors, and a new wave of Internet of Things that will really change the way humans behave, combining physical and digital worlds in a new way of interacting between humans, okay, and between humans and machines machine to machine. 3 digital twins, autonomous networks, again, will be basic elements in this future. And this means that we will have to bring new capabilities to the lab, okay? Capabilities like edge computing, so we have some, we have to extend them and sophisticate them. High capacity radio, new antennas, new features, this is normal in the evolution of mobile technologies. Evolution of the network to a cloud native environment. This is something we need to also progress significantly in 5TONIC. Need a cloud environment to host all network domains, not just radio, but also the transport and the core. Something very relevant today in the telecom industry, the capability exposure platforms, the network as a service API platforms, network slicing, the use of data and artificial intelligence, data spaces for sharing data among different operators and also operators with customers and other partners in their value chains, and as I said, time synchronization, deterministic networks. That are capabilities that will be progressively incorporated in the lab as we have use cases that requires them. Again, a lot of new capabilities. I want to go to the full list. I already mentioned quantum safe communication, multi-cloud orchestration, decentralized internet, federation and roaming services. All this will increase our capability of testing new use cases and new components. And this is just as a conclusion. We are extremely proud of what we have achieved. So we are very happy to have launched this initiative 8 years ago now. I think has delivered a lot of value, not only to the members, but in general to the industry, to Europe. I think it is a reference lab in Europe, considered a digital innovation hub by the European Commission. So this is not something easy to achieve. And we think that we have also a bright future. So we have in front of us the opportunity to keep on working on different technological developments, on new capabilities, on new use cases. And we have now a challenge that is evolving everything that we have, all this rich and advanced and complex infrastructure we have, to the next generation of technologies that have been mentioned along the presentation. And what is important is Slices RI will be, as a large research infrastructure, a very good complement to what we do in 5TONIC. So we think that basically there will be part of all these activities, part of the dream that we have for the next years, that we will be able to accomplish in the framework of Slices and also in collaboration with the Slices. And well, I think that's it.
So thank you very much, Juan Carlos. We are slightly delayed, so in principle, we will not take questions. But since we have this networking lunch, everyone is happy or invited to talk with the speakers. So thank you very much.
Thank you very much.
We pass on to the next presentation, which will be made by Professor Carlos Jesus Bernardos, and he will present the Spanish node of slices and what are the activities that are being carried out. Please, the floor is yours.
Thank you very much, Arturo. Thank you very much, everybody, for being here. I'm Carlos Granados, professor at UC3M, and I'm going to present on behalf of my colleagues, Carmen and Antonio, what we are doing to launch Slices Spain, and in particular, the Slices Madrid in the area of 6G experimentation. I would like to start with a slide that Serge used, because I think it's very, very useful and very representative of what we want to do. So this is about doing research in ICT. So okay, sorry about that. I will try to, it's not tall enough. To do research in an area that is very, very complex. I mean, even though I've been teaching mobile communication systems for some years already, and I've even been involved in the standardization of some of the protocols, I'm still amazed how a mobile network may work today. So this is a very, very, very complex thing to do research, and we need to have a set of disparate, heterogeneous, distributed skills and infrastructure to be able to do this type of research. So basically, I think this summarizes very well what we wanted to do in slices. So now I can go into the outline of what I'm going to present. I'm going to start with a very quick overview, because already Serge did a very good job in summarizing what slices is. Then I will go from slices, the whole slices research infrastructure, to slices Spain. And from there, I will focus into slices Madrid. I will first try to introduce what we built or what we leverage to build the slices Madrid, and then our design, our focus, our goals, and what we are building today. And at the end, one more thing that I'm very excited to share with you guys at the end of the presentation, but I have to wait until the end. Okay. So background. Serge already mentioned slices. For research on idiot infrastructure, we have a big gap in terms of needing infrastructure to do research on ICT. So we don't have, I mean, there are already, as Arturo also mentioned, infrastructure for doing research on other things, digital infrastructure to help doing research in other areas, but we were missing having this type of research infrastructure. And this is the delta or the gap that Slices wanted to basically fill. And initiated in 2017 with 15 countries and 25 partners. This effort basically in 2021 got into the S3 roadmap. And here you can see the map that also Serge presented with the different countries, the government support, the research and academia, and the industrial supporters. And I would like to focus on Spain. And here, basically, we have Slices Spain. There is a website that we very recently launched with all the information about the Slices Spain. This is going to be continuously updated. So, I mean, this is just the first version where you can see already some information about the Slices initiative and also about the Slices Spain and Slices Madrid. Slices Spain, as also described in the morning, is composed of two sites, Slices Madrid and Slices Cádiz, Slices in the Basque Country. And Slices Madrid is managed by India Networks and UC3M. During the rest of my presentation, I'm going to focus on Slices Madrid. And I would like to start the description of what we do, what we want to do in Slices Madrid, by basically summarizing or highlighting that we are building Slices Madrid based on our past experience providing services to the research community. And I think there are I think of course, I'm biased, but I think I'm not that much biased by saying that UC3M and India Networks has a very remarkable past experience, track record in doing projects and initiatives, providing services to other parties, to the academic community, and not only to the academic community or scientific community. And there are two sides I wanted to highlight. One is 5TONIC, what Juan Carlos has just presented, that as opposed to Slices is a private initiative, Slices is a public initiative, but 5TONIC is a leader in Europe, as you mentioned. It's a reference lab, it's a EU Digital Innovation Hub, and I think we have learned a lot of experience in validating use cases of 5G and 5G Plus in 5TONIC, providing this service to other entities. But there are also multiple EU and Spain funded projects where we have been very successful in providing services to external parties. I would like to highlight 5G Bini and 5G IF, the ICT 17 5G PPP Horizon 2020 projects that were focused into providing end-to-end 5G platforms, experimentation as a service to other entities. And there, I would like to also highlight one example of use case that we are very proud of, and I think represents very well what this type of research platforms can help or can improve into the research area and also in the societal area. And this is a use case that we did in the emergency area with SAMUR. SAMUR is basically the organism running the ambulances in the City Hall of Madrid. And they wanted to evaluate the use of 5G for a particular use case that basically consisted in monitoring a person with a device connected to 5G and automatically detecting that something happened, like a heart problem. Then automatically and without any involvement for any human, detecting what happened and trying to selecting the best team to serve that emergency in terms of location, in terms of skills, dynamically triggering that team to go to the venue. And then while that was happening, dynamically reconfiguring the 5G network so we could instantiate an augmented reality service to help the medical team support the emergency. And basically, that was done with a real 5G network, and we were using these augmented reality glasses, HoloLens. Now it's very popular because of the Vision Pro from Apple, but at that time was a very nice first test that actually helped us continue into this area of research now with the 112 Center of Community of Madrid. This, I think, is a very good example of what we have been able to do, providing research infrastructure to other partners. And that brings me to what is Slices Madrid, or what we want Slices Madrid to be. So what is Slices Madrid? Is the main site of Slices Spain. It's managed by INDEA and UC3M, so it's a set of labs. It's focused on 60+ experimentation, but again, Slices is meant to last for 20 years, so this is the beginning. But it's important also to highlight that in this area, as opposed to other S3 instruments, we need to continue or keep updating the lab to be able to basically be helpful to the community. We are already working and we have already deployed a first general service based on a standard Slices blueprint, as Serge mentioned, with a baseline 5G mobile network supporting Open RAN and leveraging open source tools or open source frameworks. This is already supported by other sites internationally, not only Slices Spain or Slices Madrid. And the idea of this is to provide flexibility in component or composing a network with RAN, edge, core, and different capabilities, and very importantly, supporting the data collection and the repository of those data into an open data repository. Slices Madrid already supports this, and it's going to extend this with particular features in deterministic networking, basically trying to bound or to guarantee bounded latency in communications, which is very important, for example, for autonomous driving or Industry 4.0, and also integrated sensing and communications, which is something that Alain Murat will talk more extensively at the end of the day. So you can see here a picture or a diagram of the blueprint that we are building. There are different components here. We have started with OpenAir interface, but we will be also trying other tools to build this 5G plus network, supporting 5G SA, 5G NSA, and then whatever evolution comes next. But then there is one more thing that we want to announce today, that we are very, very, very proud, and we were looking forward to this moment. That is the first service that the Slices Madrid is going to offer starting today. That is a satellite IoT device to do research. So I'm going to pass you the device because I have the devices here, and then I will explain so you can check yourself the devices that we are going to be using for this. And I will start by briefly summarizing the main challenges of research in IoT today. So today you want to do IoT and you want to connect things. There are two main approaches. You can use a terrestrial network, but then you may face problems with the coverage, for example, or the spectrum, or you may use a satellite network, and then you have other issues like the constellation, there is no real-time communications. Typically, it's unidirectional, and you need a large antenna. Well, we are using a solution provided by EchoStar Mobile. We have a representative of EchoStar, Brett, here, so you have more questions you can ask him during the lunch. And basically, this is the first pan-European solution supporting LoRaWAN on both terrestrial and satellite communication. So this allows us to get the best out of the two worlds in a very small form factor, as you can see in the device. As I mentioned, this provides pan-European coverage, including the sea around Europe. And you can see here, basically, the device, the research experimentation device is composed of the radio module, working on both bands, satellite and ISM, the antennas, and a Nucleo board that allows you to plug additional components, sensors, and to program the operation of the device. And as you can see, it's very small, and you can provide power by USB or via external battery, and you can build whatever research device you want to use. There is another picture. I will not go into all the details. You can see the radio. You can use that. You can collect data, process the data, and send the data either with one or the other network. You can see here basically more details about this. And then I would like to focus on what we offer. So we offer access to 54 devices. So we have a pool of 54 devices, experimentation devices, composed, as you can see, of the antenna, the radio, and the Nucleo board. We provide access to list of devices in batches from 1 to 10, although larger batches can also be negotiated, in months, in periods of 1 to 6 months, although longer periods can also be negotiated. These are free for researchers in Europe, of course. The only thing that you need to cover is the shipping cost from here to your institution and back. And of course, we provide access to the technical documentation to be able to use these devices. There is already information on the web page. You can go there already. There is a request form there that you can use. And we already got a request for doing research on this with drones to survey some maritime zones. And basically, this is what we wanted to announce today. We are very, very proud of this, and we hope we will get a lot of requests. And this is just a first glimpse. Of course, we are also working on the blueprint and the extensions of deterministic networking and ISAC. But this is another service that we wanted to announce. And with that, if you have any questions, I will be happy to address those.
So thank you very much, Carlos. Jesus will take questions at the end, as we said. And because we have this networking lunch, where it will be possible to comment. Okay. So now we are going to go to a presentation by Georg Widmer from India Networks. He's going to present a real-time experimentation platform on 6G and millimeter wave with particular emphasis on MIMO. This is not slices like 5TONIC. It's not slices. This is not slices. But I think it's interesting, so to say, complementary information. Maybe it could be provided by some slices node in the future or not. But I think it's important, like Serge said, we need to understand while we develop and build slices, what makes sense to be integrated and how to be provided. So I think it's going to be very interesting because obviously this in 6G is going to be a very, very relevant area. So please, Georg.
So yeah, first of all, thanks a lot. I'm Jörg Widmer from India Networks. I lead the wireless networking group there. We do a lot of research on wireless communications. And yes, like Arturo said, I think this is something that could potentially be a very nice component of slices. I wanted to tell you a little bit about sort of what we built and why we built it. Now, I'll go quickly over the first part because all of you are deeply involved in 5G. You know everything about sort of, well, what 5G is, what 6G maybe might be, and so on. So let me spend little time on this and much more time later on the platform. So of course, one of the big issues is really sort of the vast increase in KPI, right? Network throughput, latency expectations. And that of course also makes experimentation hard, right? So now we're getting to the point where sort of supporting 5G already is not easy on hardware. And of course we want to do 6G experimentation. So how do we get there, right? How do we get to work with hardware that offers vastly better performance and maybe gets up to the, well, beyond 256 QAM, beyond 16 by 16 MIMO, and towards these terabit throughput, 100 microsecond latencies that sort of are some of the targets for 6G, right? And now that's slightly less relevant for the audience here because, of course, slice is very much sort of 5G, 6G focused, but of course we see exactly the same for wireless local area networks. And for us as researchers, we have exactly the same issue there, right? Sort of we get access to hardware once the manufacturers actually produce these, but how are we able to experiment with these standards before they become products? Especially once we're at the point where these offer tens to even hundreds of gigabits per second in throughput, which is something we're just sort of achieving these data rates and such latencies for such physical layer hardware is extremely hard. And so that was something that we realized. We worked very much on millimeter wave communication where you run into these issues all the time. And 5-6 years ago, we started a major effort to really sort of try to build a platform that allows us to do this kind of experimentation. So for millimeter wave, very often what we've seen is that research experiments with off-the-shelf devices simply because that's what they get easy access to. And of course, that limits them very much in terms of the research that they can do. There's some preliminary FPGA-based testbeds. Unfortunately, in terms of reconfigurability and how easy it is to sort of modify them, because they push hardware so much to the limit, it's very difficult. And at the same time, they're highly expensive, not easy for research labs to afford. Maybe for industry, that's less of a problem, but for many research labs, it is. We now see sort of sub-terahertz communication pushing to terahertz communication. And again, we run into the same issues there, right? How do you even generate the bandwidth for a physical layer? How do you generate the baseband for a physical layer that supports such high data rates? Now, of course, there is very important work going on in that area already. And sort of the most important projects in that area are SRS-RAN and Open Air Interface, right? Which provide you more or less open source protocol stacks for 5G experimentation. For the research community, those have been tremendously helpful. And I guess sort of also for industry, because they're also, right, sort of, yes, you get access to hardware, but every once in a while, your labs also want to poke around deep down and then sort of being able to access really sort of any part of the protocol stack is extremely useful and is enabled by such kind of hardware. Now, we saw those solutions, we wanted to use them, and what we saw is that they do not quite do what we want them to do. They're fantastic in terms of completeness because they support the full protocol stack. But the architecture they have is that most of the processing happens on the CPU, right? Sort of basically you have AD converters, you ship off the samples, you process them, and that is inherently limited by the size of the compute cluster you can put there to do the actual baseband processing, but most importantly also by the front haul, right? Sort of how much front haul capacity do you need once you actually want to move to something beyond 5G towards 6G, right? This very quickly scales up to something that becomes infeasible. And at the moment, SRS-RAN and Open Air Interface do not support millimeter wave frequencies. They do not support FR2 yet. Open Air Interface has announced it. Hopefully that will come out sooner or later. I think it should come out this year still. I'm not quite sure what's the status of this. But given the architecture they have, that's about it. They will be able to support 400 megahertz, FR2. Maybe they can even push this to 2x2 MIMO, but it's going to be very, very hard once you want to push this to, say, 16x16 MIMO and wider bandwidth, right? Just from the architecture they chose, that's going to be extremely hard. And so what we see is that, well, from a flexibility perspective, of course, it's very easy. You do direct RF sampling with any sort of like analog to digital converter, and then you move functionality to software and do the processing there. And of course, like I said before, what really becomes the bottleneck is the front haul. This works well for moderate bandwidth and sort of reasonable MIMO orders, pushing this to 6G. That's where it becomes more difficult. And so here, we already see this in 5G, 6G. You're very well aware of this, so let me just very quickly go through this, right? Sort of from 4G to 5G, now you have disaggregated baseband units with the CU, DU, and RU. And directly connected to that, all the different functional splits, where you can play with sort of how much do you have in software in the cloud? How much do you have directly in hardware on the base station? And where do you have your front haul and basically ship the samples off to sort of then be processed at the higher layers? And so the more you move the functional split to the right, the more you have in hardware, the easier it is to push performance. And of course, also the harder it gets to experiment with it because everything is implemented in hardware rather than in software. Very important, especially for experimentation, and I guess you know these functional splits probably very well, is sort of the ones around sort of split 7, 7.1, 7.2, 7.3, which sort of seems to be a nice sweet spot where sort of some of the functionality, of the important functionality to reduce the requirements for the front haul are in hardware on the base station, and a lot of the complex operations that are not so critical in terms of processing capabilities, but still sort of a hassle to implement. And for that reason, it's nice to do it in software, can then be in the centralized unit. These are the front haul bit rates. And you see those go down drastically. So split 8 is basically where you do everything in software. You just ship off the IQ samples directly. And this is where sort of quickly you run into issues with the front haul capacity. And then they go down as your functional split becomes, basically higher and higher in that case. Now, what we focused on really was to build an experimentation platform that on the one hand side provides you with the flexibility to instantiate different kinds of solutions, right? Have more in software or more in hardware depending on what you need in terms of performance versus flexibility, right? Depending on which part you want to touch. Maybe it's much easier to do that if it's in software, provided performance-wise you can afford that. And so we started out, like I said, 5 years ago. Around that time, a very suitable hardware came out, the RF socks from Xilinx, which are sort of very nice, very powerful FPGA-based software-defined radios that from the onset have the capabilities to support beyond 5 GNR FR2 sort of bandwidths and MIMO orders. So we started out with a memory-based design just because that's the easiest to support for experimentation. So that's basically your functional split 8, where sort of we do everything in software, and in hardware we just get the samples and store them in memory. And that the nice thing is you can connect that to MATLAB. You want to test new waveforms and so on. Fantastic. The nice thing with that hardware is that performance-wise, we could do this with up to 8x8 MIMO at sub-6 gigahertz frequencies with up to 1 gigahertz of channel bandwidth, right? So that's 8 gigahertz combined baseband bandwidth. No standard like has 1 gigahertz bandwidth at sub-6, but at least in theory, that's what you could support. And at millimeter wave frequencies, we have 4x4 MIMO with currently up to 2 gigahertz of bandwidth per channel. And this, depending on the front end, we have various different front ends. Now, this is all something where we don't build the hardware, we build the software. So we basically built the FPGA implementation for all of this that was sort of highly performance optimized. And you can get the RF socks, of course, from Xilinx and various antenna front ends. Those are, for example, from Sivers, from which we have 60 gigahertz and 28 gigahertz front ends, 24 as well, or sub-6 gigahertz sort of normal dipole antennas. And given the flexibility of that platform, you can even have mixed setups, right? Sort of you can build your base station that from the same baseband unit supports, in this case, 2x2 MIMO at millimeter wave frequencies, 28 gigahertz, plus 4x4 MIMO at sub-6 gigahertz, driven by the same baseband unit. Not going to go into the details. The main complexity here from the research perspective was really sort of how do you make the hardware underneath efficient enough to push all those samples through at the line rates that such sort of MIMO orders and bandwidth require. Now, for many applications, you need closed loop operation. I'm going to get more into the details there later on. like as a first very simple thing, what we did is provide a feedback channel to be able to do channel estimation and beam training, right? So a very simple example is that you need to update your antenna patterns as the user moves, or to do beam training. And for that, of course, you need a feedback loop. So we have a number of hardware accelerators directly implemented in hardware. One thing that's very important is the packet detection, because storing IQ samples is extremely costly in terms of memory. At least you want to make sure those are only the ones from properly detected packets. You don't do that for noise. We have channel estimation and beam tracking for 4x4 MIMO with the control loop to basically update the beam patterns as the channel estimates change. And we have nanosecond level antenna reconfiguration capabilities. And here's a very simple example with real-time beam tracking on this platform, right? So basically we have a transmitter, we have a UE that moves laterally. And of course, because we have very narrow beams at that frequency, you need to update the beam patterns directly on the platform with the feedback loop that we have in hardware. And then what you see is, doesn't work. So what you see is here, sort of as the angles change, the beam patterns track this, and the beam pattern that's selected, that is the thick line here, is the best out of all the possible beam patterns that you see as these thin lines. So basically just to show that sort of this feedback loop works, you can update your beam patterns in real time and have real-time channel estimation. Now, this was the first version of the platform that we built. At the moment, we're hard at work of basically making this 5G ready and supporting various different functional splits. And so currently what we support is a receiver platform. On the one hand side, we support one instance, one numerology for FR1, which is basically 30 kilohertz subcarrier spacing for sub-6 gigahertz frequencies, and 240 kilohertz subcarrier spacing for FR2 millimeter wave, for two different bandwidths, 40 megahertz for FR1 and 400 megahertz for FR2. That is a full receiver physical layer receiver implementation. That's already sort of up and running, and of course it's sort of just implementation effort to sort of support further numerologies. The platform is there. It's just sort of we wanted one thing to get up and running first before we extend this. Now, we already had the software implementation, and now we have the hardware implementation. And now the nice thing is basically with this receiver, you can support any functional split you want. It's just a matter of where you sort of take out the samples. So you have your signal coming in from the antenna, goes to the AD converter, then basically through to do the FFT, channel estimation, and so on and so on. And for all of these, you have sort of hooks to then move the rest of the processing to software. And that's basically sort of the first step towards then flexibly supporting different functional splits with the same hardware. And you, like, at some point, we'll be able to actually reconfigure this in real time. That's something we're building at the moment. One thing that's very nice with the RF SoCs as well is that sort of LDPC coding, which is one of the really hardware intensive or computational complexity intensive things, is already natively supported on these with sort of special purpose hardware. So in terms of the performance you get out of the system also, that's very useful. Just to show that this works, right? So these are tests that we did over the air at millimeter wave frequencies with 417 megahertz of bandwidth. And one example, the red curve shows the decoding in hardware, and the blue curve, so basically red curve decoding fully the phi in hardware, blue curve decoding fully the phi in software, and it's basically the same. On the right-hand side, you see the corresponding constellation diagrams. That's the receiver. Of course, you need a transmitter. That's what we're currently working on. At the moment, the transmitter is still memory-based, right? So we prepare a packet to be sent, a waveform to be sent. We just store that in memory, then the transmitter pushes out. And of course, we need that functionality in real time on the hardware as well. That's what's currently being implemented, and it shouldn't take too much longer until that's ready. Now that we have the receiver, of course, the transmitter implementation is way faster, way easier to actually realize. Now, what we can also do, what we already have experimented with, is actually full duplex. The baseband unit, of course, supports that anyway, but the nice thing is that the antennas that we're using, they also support that, at least at millimeter wave frequencies, because at millimeter wave, what we found with these antennas is that if you design well enough beam patterns, even without interference cancellation, just from the spatial separation of the antennas and using directional beam patterns, the self-interference is low enough that you can actually operate them in full duplex. What we're also currently working on is, of course, that's the PHY. You need the higher layers, and that's sort of a big part of well, the functionality to make this a useful platform. And that's what we don't want to implement ourselves. Of course, like Open Interface, SRS-RAN, they've put a huge amount of effort into implementing that. What we're currently working on is connect the higher layers of SRS-RAN, so MAC and above, to our platform so that in the end you will have sort of a full stack solution. Now, as I said before, we did this not just to have the same as Open Interface we'll hopefully have at least next year. The whole point was to start with a design that's highly scalable on a platform that allows to move beyond 400 megahertz. So we've already done experiments with we already have done experiments with 4 gigahertz of bandwidth. Now, unfortunately, we don't have an antenna front end. So this is an over-the-wire experiment. We just generate the baseband. 4 gigahertz antennas will become available for millimeter wave frequencies as soon as 802.11ay hardware becomes more widely available. We also intend to test this with some colleagues in the US who have sub-terahertz test beds, where, of course, 4 gigahertz is nothing. We'd much rather have sort of 10 gigahertz of baseband. And so that's another direction that we're trying to push to. And one area also, I guess, that Alain is going to talk about later on, we do a lot of research on joint communication and sensing, integrated sensing and communications. And for that, of course, such a platform is highly useful, especially, again, because you have access to everything, right? So you want your IQ samples directly at full bandwidth for all the MIMO streams, no problem at all, right? If your memory bandwidth allows, you can access all of this and then later on process it offline or directly online. So terahertz communication is one very interesting direction, we think, for this platform. We currently need the hardware still to support this, right? So new RF SOCs, more powerful RF SOCs are coming out. And basically the goal there would be to try to move towards sort of 10 gigahertz of baseband. There are various solutions to do this with sort of multi-ADC sample interleaving. Silex is already working on this. There are also other platforms coming out, especially from AMD and Intel, with sort of FPGAs and very powerful AD-DA converters integrated that we are looking at to see which platform would actually support this, like from the hardware side, from the FPGA side. This I briefly mentioned before already, right? So that's one use case where we use the very high resolution given to us by the high bandwidth channels for the sensing part. We have a real-time capabilities of the platform. So basically you can do your sensing directly in real time as the samples come in. And we had a range of papers already, sort of just to briefly mention that, right? Sort of now, given the high spatial resolution that you have, you can, for example, detect fine-grained microdoppler that's created by humans as they walk, right? Sort of how the arm moves relative to the body, with which the centimeter level resolution of millimeter wave signals allows you to get, right? Allows you extremely accurate estimation of what is going on in your environment from the base station, right? Sort of how many persons are in the room, what are they doing, in what poses are they in, or in a city scenario, right? What cars are driving by. What are their engines? Because a diesel engine vibrates different from a petrol engine from an electromotor, right? So there's a lot you can get from these very, very fine-grained measurements. And I think here we're just at the beginning of what you can actually do. And of course, machine learning, that's another thing that's extremely interesting, where again, sort of it's interesting to have access to all the different sort of parts of the phi and the higher layers in order to sort of integrate machine learning there and be able to sort of, one of the things we look for example, is then to sort of do a machine learning based physical layer and directly sort of, one thing that we're considering now is directly integrating that on the FPGA, because of course, performance-wise, that would require a sort of a very high performance machine learning-based inference engine that can do phi processing directly in real time. So with this, let me conclude. I'm going to be around at least for until the lunch time. So if you have interest in this platform, please contact me or shoot me an email. We'd be very interested in sort of getting that out, getting other people to use it. Because of course it's been a massive development effort. We think it could be quite useful for others to do experimentation on it. Thank you very much.